In this video, we will explore trends in acidity as it relates to chemical structure. Acid strength is determined by the equilibrium shown here. The stronger the acid, the more hydronium ion is formed when compared to a weaker acid. Thus, a stronger acid has a larger Ka and subsequently a lower pKa. The golden rule when it comes to explaining trends in acidity is the following. The stronger the acid, the weaker the conjugate base. You will typically be comparing the strength of two acids. In order to explain the acidity, you will have to be able to explain the relative stability of the conjugate bases. But before we do that, the fact that HCl is a stronger acid than HF means that the conjugate base, the chloride ion, is more stable than the fluoride ion, because the stronger the acid, the more stable the conjugate base. The first trend we will look at is the relative strength observed in the binary halogen acids, HF, HCl, HBr, and HI. Again, the stronger the acid, the more stable the conjugate base. So we must first write down all of the conjugate bases and explain their relative stability. The observed trend is that acid strength increases as we go from HF to HCl to HBr to HI. This means that HI has the largest Ka in the series, while HF has the smallest. This trend is reversed when comparing pKa values. So in terms of conjugate base stability, I- is more stable than Br-, which is more stable than Cl-, which is more stable than F-. Now we must be able to explain the trend in conjugate base stability. The most obvious structural difference between the conjugate base ions are their relative sizes. We know that I- is the largest in the series, while fluoride is the smallest. So how do we explain that the larger ion is the more stable ion? The answer is charge density, which is related to polarizability, which was discussed in the intermolecular forces video. Charge density is the charge per volume ratio. The less charge dense an ion is, the more stable it is. Since I- and F- have the same charge, but I- is larger than F-, I- has a lower charge density and is therefore a more stable conjugate base. Remember, a base can be defined as an electron pair donor, so the more spread out the negative charge is over the volume of the ion, the less reactive it will be. Another accepted argument is based on bond strength. An acid can be defined as a proton donor. Hi is more likely to donate H+, since the Hi bond is larger and weaker than the HF bond. The next trend we will look at is a series of acids where the conjugate bases are in the same period or row of the periodic table. HF is the strongest acid in the series, therefore F- is the most stable conjugate base. When we draw the conjugate bases, we notice that the negative charge all reside on elements in the same period. Therefore, their difference in size is negligible and doesn't explain the observed trend. Stability of the conjugate bases in this case is determined by electronegativity. In bases where the negative charge resides on atoms of similar sizes, the more electronegative the atom, the more stable the conjugate base. Since electronegativity increases from C to N to O to F, it can be argued that F is the most stable with a negative charge, while C is the least stable in the series. Next, we will look at trends where the atoms containing the negative charge are the same in the conjugate bases that we are comparing. In these cases, stability will be determined by either resonance or the inductive effect. Let's compare HNO3 to HNO2 and predict which acid is stronger based on their relative conjugate base stability. Shown here are the resonance structures for the conjugate bases of both acids. In both cases, the negative charge resides on an oxygen atom. Since the NO3- ion has more resonance structures than the NO2- ion, NO3- ion is more stable than the NO2- ion. The more delocalized the charge, the more stable the conjugate base. Since the NO3- ion has more resonance structures, it can more effectively delocalize and spread out the negative charge. So the NO3- ion is more stable than the NO2- ion. That makes HNO3 a stronger acid than HNO2, because the stronger the acid, the more stable the conjugate base. So, when comparing two acids, if the conjugate bases have the same atom containing the negative charge, the conjugate base with more resonance structures is more stable. The last trend we will look at is between acids where there is no difference in size, electronegativity, or resonance structures when comparing their conjugate bases. In these instances, the inductive effect will allow us to predict the relative stability of the conjugates. The presence of a dipole within the conjugate base allows for a degree of stabilization between the negative charge and the positive end of said dipole. This stabilizing effect is called the inductive effect. The trifluoroacetate ion is more stable than the acetate ion due to the inductive effect. Since the more stable conjugate base has the stronger parent acid, trifluoroacetic acid is a stronger acid than acetic acid. In conclusion, when asked to explain a trend in acidity, always start by stating the following. The stronger the acid, the more stable the conjugate base. Then make sure to draw the conjugate bases. The following is generally true. If the negative charge resides on atoms that are in different periods, for example F- versus Br-, then the conjugate base with the larger atom is more stable. If the negative charge resides on atoms that are in the same period, F- versus O-, for example, then the conjugate base with the more electronegative atom is more stable. If the negative charge resides on identical atoms, then the conjugate base with more resonance structures is more stable. If the negative charge resides on identical atoms and has the same number of resonance structures, then the inductive effect is what will determine stability.